So you've seen in previous videos how we can use differentiation to work out maximum and minimum values, and so it means that we can use it to optimize a problem. So by finding the stationary points of a function, we can determine its maximum or minimum value for a particular set of conditions, and we can use that information to optimize. So in this example, we've got a glass front of a carriage clock has a breadth of x centimetres. The jeweller has used 16 centimetres of gold leaf to edge the perimeter of the glass. And in part A, we want to find, in terms of x, expressions for the height of the glass front and the area of the glass. In part B, we want to find the dimensions of the rectangle that give maximum area. And in part C, we want to calculate that maximum area. So going back to part A, we want to find, in terms of x, expressions for the height of the glass front and the area of the glass. Now, from the question, it's telling us that the jewellers used 16 centimetres to edge the perimeter of the glass. So that's the distance around the face of the carriage clock. Now we want to find, in terms of x, an expression for the height of the glass. So we're going to let the height be y, because we know that the breadth is x. And then we can come up with an expression for the perimeter, because we know that P equals 2 multiplied by x plus y. And that's going to equal 16. So if we do some rearranging, because we want the height y in terms of x, we can divide both sides by 2 and get x plus y equals 8. And then we're going to take away x from each side to get y equals 8 minus x. So we've now got an expression for the height of the glass. Now the other part of part A was the area of the glass, and we know that the area of a shape is the breadth times the height. And so we can work out that the area A equals xy. And if we replace the y with our 8 minus x expression, so that we have the area in terms of x, it's x upon 8 minus x. And if we expand the bracket, we get A equals 8x minus x squared. Now part B asks us to find the dimensions of the rectangle that give the maximum area, and so we're going to need to differentiate our formula for our area in order to be able to work out what the stationary point would be. So we know that the maximum area is when a dash x, or the derivative of the area, equals 0. So from the previous slide, we got a equals 8x minus x squared. And so the derivative of a with respect to x is going to be 8 minus 2x. And we're going to make that equal to 0 to find out the maximum value of x. And doing some rearranging, we're going to end up with x equals 4, and our units are centimetres. Now we have to do a nature table, because we need to explicitly show that this is a maximum turning point. So we need to look at the numbers before 4 and after, and consider the derivative and the slope. So we know when x equals 4, the gradient is 0. If we consider 1 before 4, we'll have a positive gradient, so our slope is going up. And if we consider 5, we're going to have a negative gradient, so our slope will be going down. So we've demonstrated that we have a maximum stationary point. So the maximum is going to be at x equals 4 centimetres. And y is going to equal 8 minus x. And so 8 minus 4 gives us a y value of 4 centimetres. So the dimensions, because that's what we're being asked for in part B, of the front face of the carriage clock are 4 centimetres by 4 centimetres. And part C asked us to work out what that maximum area is. And so all we need to do is multiply our maximum dimensions together. So the maximum area is going to be 4 times 4, giving us a value of 16 squared centimetres. Now sometimes we cannot solve problems directly. Sometimes we need to find an expression for a value provided and use it to obtain a function that can be differentiated in order to be able to optimize the problem. So in this example, the volume of the square-based glass display case shown is 500 cubic centimeters. The length of the base is x centimeters. The base of the case is not made of glass. And we want to show that the area of the glass in the case is A equals x squared plus 2000 over x. Now we've been given the volume in the question, it's 500 cubic centimeters, and we know that V equals LBH. Now the question also tells us that the length of the base is x centimeters, and that base is a square. So we know that the length is x, and the breadth is also going to be x. And we're going to let the height be the variable y. So now that we've got the dimensions of the cuboid, we know that V equals LBH, and that equals 500 cubic centimeters. And we're going to substitute in our variables. So we have V equals x multiplied by y equals 500. So that gives us x squared y equals 500, and expressing the height y in terms of x, we get y equals 500 over x squared. Now the question's asking us to show the area of glass, and we know that the base is not made of glass, so we've got the top of the case, and the dimensions of the top of the case are x by x, so the area of the top surface, and we've got one of these, is going to be x squared. And then we've got four equal-sized rectangles that go round the four sides of this glass display case. So we've got four rectangles that are x by y in dimension. And if we put that into our area formula, we know that A equals xy, and we can substitute in our value for y, which was 500 over x squared, and that gives us an area for those four rectangles of 500 over x. So the total area, AX, equals x squared plus 4 multiplied by 500 over x, and that gives us an area of x squared plus 2000 over x, which is what we've been asked to show in the question. Now part B asks us to find the dimensions of the case that minimize the use of the glass, and then to calculate this minimum area. So this is an optimization question, and in order to do this, we're going to have to differentiate our formula that we've created for the area of our display case. So we know that the minimum area can be found by the derivative of the area with respect to x equaling 0, as this is the stationary point. So area equaled x squared plus 2000 over x. We need to put this into a differentiable format. So x squared plus 2000 times x to the negative 1. And now we can differentiate it with respect to x, giving us 2x minus 2000 times x to the negative 2. Now we're going to rewrite that with positive indices because it's going to make it easier to solve. So we've got 2x minus 2000 over x squared equaling 0. And that means that 2x is going to equal 2000 over x squared. And we're going to multiply both sides by the fraction. So we're going to end up with 2x cubed equals 2000. Divide both sides by 2 gives us x cubed equals 1000. And if we cube root 1000, we get 10, and our units are centimetres. Now we have to explicitly show that this is a minimum because it's an optimization question, and we're going to do that using a nature table. So we're looking at values of x leading up to 10 and beyond 10. And then we're considering what happens to the derivative and what the slope or the gradient is going to look like. So at x equals 10, the gradient was 0 because it's a stationary point. Considering 1, the derivative evaluated is going to give us a negative value, so therefore a downward slope. And considering 11, beyond 10, we're going to get a positive value, which is going to give us a positive gradient. And so you can see we've explicitly shown that at x equals 10 centimetres, we have a minimum value. Now the question asked us for the dimensions of the glass display case. So if we draw ourselves a sketch of that cuboid, we know that the base was square, so it was x by x, and the height we gave the variable y. And we created the expression for y in terms of x of y equals 500 over x squared. And so at x equals 10, y is going to equal 500 over 10 squared, giving us a height for our glass display case of 5 centimetres. So our display case is going to be 10 centimetres by 10 centimetres by 5 centimetres. So the minimum area for our display case can be found by taking the expression for our area, which was x squared plus 2000 over x, and finding out the value of A10 by substituting x equals 10. So we've got 10 squared plus 2000 over 10. And so the minimum area of our glass display case is 300 squared centimetres.